Starting it now. Hi, good evening, everyone. My name is Nell Pepper, and on behalf of Harvard Bookstore, I am so pleased to introduce this virtual event with Jeremy DeSilva presenting his book, First Steps: How Upright Walking Made Us Human, in conversation with Kate Wong. I hope you're all well and safe. Thank you so much for joining us virtually tonight. Through virtual events like tonight's, Harvard Bookstore continues to bring authors and their work to our community and to our new digital community during these challenging times. Every week, we host events here on our Zoom account. And just like always, our event schedule is on our website at harvard.com, and you can sign up for our email newsletter for more updates. This evening's discussion will conclude with some time for your questions. If you have a question for our speakers at any time during the talk tonight, please click on the Q&A button at the bottom of the screen or wherever it happens to appear on your Zoom platform, and we will get through as many as time allows. In the chat, I'll be posting a link to purchase copies of First Steps on harvard.com, as well as a link to donate in support of this series and of our store. Your purchases and financial contributions make events like tonight's possible and help ensure the future of a landmark independent bookstore in Harvard Squares. We thank you so much for tuning in and showing up both in support of this series and of the store and of the truly fantastic set of booksellers at Harvard Bookstore. We sincerely appreciate your support now and always. And finally, as you may have experienced in virtual gatherings, technical issues may arise. We hope they don't. If they do, we will do our best to resolve them quickly. We thank you so much for your patience and understanding. And now I am delighted to introduce our speakers. Jeremy DeSilva is an anthropologist at Dartmouth College and editor of is the editor of A Most Interesting Problem: What Darwin's Descent of Man Got Right and Wrong About Human Evolution. He is part of the research team that discovered and described two ancient members of the human family tree, Australopithecus sediba and Homo naledi. He studied wild chimpanzees in Western Uganda and early human fossils in museums throughout Eastern and South Africa. From 1998 to 2003, he worked as an educator at the Boston Museum of Science. Kate Wong is senior editor at Scientific American. She has been writing about the evolution of humans and other organisms for the magazine since 1997. She is also co-author with Donald Johanson of Lucy's Legacy: The Quest for Human Origins. Tonight, they'll be discussing Jeremy DeSilva's new book, First Steps: How Upright Walking Made Us Human. In it, DeSilva explores the history of bipedalism, the ability unique to humans among living mammals to walk on two legs. He makes the case that bipedalism was the crucial change that allowed for the evolution of humans despite the difficulties it posed to the genus Homo forever after. Publishers Weekly praises DeSilva's love of fossil discovery and of collaborating with colleagues comes through in the wonder he experiences in examining bones firsthand. His ability to turn anatomical evidence into a focused tale of human evolution and his enthusiasm for research will leave readers both informed and uplifted. I am so pleased to turn things over to our speakers. The digital podium is yours, Jeremy and Kate.
Thank you, Nell. I really appreciate the introduction. Hi, Kate. Thanks for
Hi,
being here and doing this.
It's great to see you. Thanks so much, Nell and Jerry, and to the Harvard Bookstore. I'm delighted to have the opportunity to pepper Jerry with questions about his fabulous new book, which is about all the things that I get most excited to write about. So it's really a pleasure to be here. And I thought maybe, Jerry, if you're up for it, we could sort of kick off the conversation by having you tell us why, humans have a number of traits that set us apart from other mammals, from other primates. We have naked bodies, we have large brains and language. So why focus on bipedalism?
Well, it's a great question. Right, like you said, we have these differences. We have lots of similarities to our mammalian cousins and our primate cousins and our ape cousins, but we have these differences as well. And upright walking is one of those. Mammals fly and swim and sprint and leap. Mammals knuckle walk and climb. Your typical mammal moves around on all fours. Think about a cow or a goat, sheep, dog, cat, squirrel, moves around on all fours. But only humans will navigate the world on their extended hind limbs all the time. It's a really strange way to move. And when another mammal does it, we kind of lose our minds. We take out our cameras, we videotape what's happening, we post it to YouTube, and it gets millions of hits. I was in researching this book, I found examples of bears moving on two legs in New Jersey. There's a bear named Pedals. And there have been almost 5 million views of a bear walking on two legs through this New Jersey suburb. A gorilla in the Philadelphia Zoo, Lewis, started walking on two legs occasionally, not frequently, just occasionally. Someone got a video of it, and it ended up on the CBS News. And so something that we do all the time, we even use the word pedestrian, right, to describe something ordinary. When another animal does it, it's remarkable. But not only that, the fossil record, which is what I work on. I'm a paleoanthropologist, so I study fossils, and what we can tell by going back in time to the common ancestor that we shared with our ape cousins. The further back we go, we start to lose some of those unique characteristics, right? The large brain, evidence for language, art. Those things happen more recently. Stone tools. What's the most ancient characteristic we think on our lineage is this ability to move on two legs. So not only is it really strange as a mammal, but it's the most ancient thing that we evolved. It sort of set our lineage off. And what I argue in the book is that it was the key innovation that led to many of those other anatomical and behavioral changes that make us human.
Yeah, that's great. It's a really interesting lens through which to view the entirety of human evolution in a sense. This might sound like a weird question, but thinking about this from a biomechanics standpoint, upright walking, we do it all the time. We kind of take it for granted, and we don't really think about it. So what is special about it from the standpoint of biomechanics? Like when you describe the act of walking on two legs, and what's unique about it, how do you sort of convey that?
So it's a balancing act, moving on two legs. Think about what I talk to my students about is, all right, imagine if I gave you an assignment to design me a chair. You'd probably design it with four legs. And if, there might be some clever students that make a bar stool, right, and make it out of three legs. But if you make a chair out of two legs, it's probably not going to work. And I'm going to sit in it and fall over, and the student will fail the assignment. Two-legged locomotion is a pretty unusual way, again, for a mammal to move around the world today. Now, we can get into bird locomotion at some point, and then deep in the past, we find evidence of bipedalism in dinosaurs and even in an ancient crocodilian lineage, which is really fun to think about. But from a biomechanical standpoint, this is about balance. And what we can see, and one of the ways we can identify fossils as coming from things that are adapted to move on two legs, is because they have these specific shapes to them, these individual bones that would align the joints in a way that would prevent us from tipping over, or would change the action of certain muscles so that those muscles would act in a way to, again, prevent you from tipping over. One of the classic examples is at the hip joint, that when you take a step and lift your other leg, you fall over. And when a chimpanzee walks on two legs, that's exactly what they do. They wobble from side to side. But in humans, we've evolved a pelvis. So here's a human pelvis. We've evolved a pelvis where the muscle attachments here have wrapped around to the side of the body. And by being on the side, they then will counteract that tilt every time you take a step. So if you find this part of the body and it looks like this, you can tell you have something moving on two legs. So, Kate, Lucy very well. Here's Lucy's pelvis. And sure enough, she's got those ilia, or the hip joint, arranged in a very human-like way. So even if this was the only part of her we found, we would be able to tell that she was able to balance on a single leg And why else do that unless you're moving around on two legs? But from a biomechanical standpoint, and really, connecting it to natural selection, it's not a great way to move around your world.
Right.
We are incredibly unstable on our two legs. We fall a lot, and that can be quite dangerous. There are 30,000 Americans who die every year falling, um, and in addition to that, we are stunningly slow for a mammal. Usain Bolt, the fastest human who, as far as we know, has ever lived. The fastest he ever ran was 28 miles an hour in his 100-meter dash in 2009, his world record 100-meter dash, 28 miles an hour. And it sounds impressive, and it is. I couldn't come close to that, right? But it's half the speed of a galloping zebra, half the speed of a galloping antelope, and perhaps more importantly, half the speed of a lion and a leopard. So evolving this form of locomotion made us slow. And so
Right.
it raises some really interesting questions of how, in what ways was this beneficial, and allowed us to overcome some of those maladaptations, I suppose you can even frame it as, this lack of speed.
Yeah. Yeah. I mean, you anticipated my next question, which is, why evolve this kind of what seems on the surface to be a subpar way of getting around? And so, I know there's been a lot of scholarship over many decades, and with people coming up with all kinds of ideas about why we did come to have this unusual kind of locomotion. And there's some really interesting ideas going back as far as Lamarck and Darwin, and I thought it would be fun to kind of just take a nickel tour through some of those ideas, if you wouldn't mind indulging us.
Yeah, it's one of those things where, if there was another mammal that moved on two legs regularly, we'd be able to test this more effectively. We'd be able to do some science and say, okay, what does this other mammal do? What does it eat? Or what are its mating patterns? Or what ecology does it live in that in which this form of locomotion is beneficial? And so, as a scientist, when you're trying to figure out something about yourself, you always want to look out into the natural world and say, all right, where else do we see examples like this? And the fact that we don't have other mammals that habitually walk around on two legs makes this a really, really difficult scientific problem to solve. And it's one of the reasons that we haven't solved it, and that you can go back to Lamarck and take it right up until 2021. People are still hypothesizing why bipedalism was selectively advantageous for our ancestors. So, right, you've got ideas about seeing over tall grass, and that goes back to Lamarck. Lamarck was very interested in humans being able to stand and see off into the distance. And with that one, if you look off into the distance and you see a predator, the worst way to get away from it would be bipedally. You'd want to be down on all fours and gallop away because you'd be much faster. And so that one has never made any sense to me. There are ideas about, of course, Darwin saw this connection between our small canine teeth, our bipedalism, and tools. That this was about freeing the hands for tools. And that becomes somewhat problematic, although I think it's an interesting idea worth revisiting. But it becomes problematic because of the timing. That we have evidence for bipedalism, in hominins that are 6 and maybe even 7 million years old, terrestrial bipedalism, and we don't have evidence for stone tools until about 3.3 million years is the oldest reported evidence for stone tools. And then there are wild ideas about displaying genitalia, that this was some sort of showing off your body for selection. There are ideas that are a little more reasonable and testable, having to do with food sharing. And if you can free the hands not to make weapons or tools, but to gather food, there are some ideas that have been promoted where the females are gathering food and sharing it with others. It's Adrian Zillman and Nancy Tanner's idea. And then Owen Lovejoy flipped that and argued it was the males that were collecting the food and sharing it with potential mates. an idea that has had a little maybe more lasting power has been about energetics. That moving on two legs, yes, we're slow, but we are energetically very efficient. And one of the best ways to explain this is Herman Poncer and I talked about these ideas, and he said that in order to lose a pound of weight, you'd have to walk about 70 miles because we're too good at it. We're too energetically efficient, and so now, you know, you don't want to lose weight if you're an early hominin, but if you need to get enough food to survive, and maybe there's not a lot on the landscape, those individuals who are moving in a way that's energetically efficient might survive a little better. And so that's a possible idea as well. Yeah, there are lots and lots of hypotheses. And we still don't have a handle on it, and that's okay. You know, there are going to be plenty of things that new fossil discoveries, going to allow us to go back and revisit some of these ideas and retest some of these ideas. And really, the issue for me is not figuring out which one is right. It's beginning to narrow that list down and eliminate the ones that are clearly wrong. That's how science works, by refuting ideas rather than proving them.
Right. So we don't know yet why bipedalism evolved, but we do have a lot more information than we used to about the time frame in which it evolved. So, you know, maybe we could kind of talk about some of the fossil discoveries that have really kind of allowed you and your colleagues to start to piece together when this all happened, and you know, what bipedalism might have evolved from, and where it took us.
Yeah, so you know, a lot of folks listening will probably know about Lucy, discovered in the 1970s, and Lucy is just a magnificent partial skeleton. I've got her back here, or a cast of her. The original is in Ethiopia, of course. And then not long after Lucy was discovered, there were footprints found at the site of Laetoli in Tanzania, where I do some of my research as well. And that pushed bipedalism back to about 3.5 million years ago. So those were remarkably important discoveries showing that human-like bipedalism existed, you know, 3.5 million. And yet the genetics would point towards a common ancestor that we shared with chimpanzees at about 6 or 7 million, that the split between the two lineages was probably complete by 6 million years. That's a big gap, 3.5 million to 6 million. What's going on in that time frame? And in the last 20 years, there have been really remarkable and wonderful and important discoveries that have been made that begin to piece that story together. One is a partial skeleton like Lucy from Ethiopia that's 4.5 million years old, known as Arti, or Ardipithecus ramidus. And Ardipithecus has some of the key morphologies of the pelvis and the foot that would indicate that at least was occasionally able to move around on two legs when it was on the ground. But it also has a big grasping toe in the foot. So this is an excellent tree climber, long curved fingers. It's a really good tree climber. But when it came down to the ground, did it knuckle walk? No, it appears it didn't. It could actually move on two legs. So that's 4.5 million now. We've got something that's bipedal. And then if you go further back than that, the evidence becomes a little much more controversial and a little more difficult to interpret. So this is a toe bone from a 5.5 million year old hominin from Ethiopia, and it matches the shape, especially the end of the bone, of a human toe that would push off the ground when you're walking, whereas a chimpanzee, the toe actually curves in the other direction for grabbing. And this has a curvature to it that's more like an ape. So it definitely had some time in the trees, but it has an angulation to its base that's like yours and mine, meaning it would probably have been able to push off the ground. So this is a cool fossil, but it's just a toe. It'd be nice to have more. Here's a beautiful femur from Kenya that's 6 million years old. And what's unique about this one if you compare it to a chimpanzee, here's a chimpanzee, the head or the ball part of the hip joint, very similar, but look how short the neck is on the chimp and how long that neck is on this fossil. And what that would do, it's similar to what I was talking about earlier of repositioning those hip muscles so you could balance on a single leg. By drawing those muscles farther from the hip, you're making them more efficient. And we think that that anatomy is evidence for bipedal locomotion in what we would call Auroran. This is a fossil from Auroran. And then if we go back even farther than that to 7 million years, there's this remarkable skull that was discovered in Chad and is very controversial. The researchers who found it and first interpreted it argued that the hole at the base of the skull where the spinal cord would exit the brain was in a very human-like position. And therefore, this creature would have been able to hold itself upright and maybe even walk on two legs. We don't walk with our heads, so I'd like to see fossils from other parts of the body. And there is a femur now that has been published by one team, and then another team has a preprint out, and they come to completely different conclusions on whether this is an upright walker or not. And to me, that I mean, as you converge on the common ancestor of humans and chimpanzees, you're going to get something that is not quite like any of the living apes, and is a fabulous combination and maybe a frustrating combination of anatomies that are difficult to interpret. It's kind of what you might expect in a common ancestor.
So do you think that this femur looks like that of a biped, or no?
Well, I've not been able to hold, I like to talk about fossils I've been able to see. And this is not a fossil that I've been able to see myself. However, there are even older fossils now that are, we don't have much from 8 million, 9 million, 10 million, but there's this new discovery from a site in Germany. And Germany sort of might sound, surprising to some of the folks listening, because we've been talking about sites in Africa. But in the late Miocene, apes expanded all around the Mediterranean, what is today the Mediterranean, and we're living in forests in Southern Europe. So we find ape fossils in Spain and France and Italy, Greece, Germany, Turkey and Hungary. This new fossil from a creature called Danuvius from 11.5 million year old deposits in Germany looks like it's very upright. And to me, that's a really interesting find because it could imply, and we're still trying to figure this out, it's one of the hottest topics in our field right now, of what is the body form from which bipedalism evolved. There are a lot of t-shirts and coffee cups and bumper stickers that would suggest a chimp turned into a human, right? And chimpanzees are not our ancestors, they're our cousins. And the common ancestor is an ape that we branched from, but so did chimps, and chimps have evolved too. And so it's not a given that common ancestor was a knuckle walker. And some of the fossils that we're finding in those Miocene deposits might indicate that the common ancestor was actually more upright in the trees, and that knuckle walking could be a more derived form of locomotion. There are plenty of researchers, plenty of my colleagues that would disagree with that and think that knuckle walking is the form from which bipedalism evolved, and they've made compelling cases for that. We need more fossils to figure this out.
It's a really revolutionary idea, so it's fun to think about that. Now, if bipedalism is a uniquely hominin trait, and Danuvius at 10 million years old is a biped, is Danuvius potentially a hominin?
So I don't think so. I don't think the timing is right, and I think that I think the genetic data show very clearly when these lineages were branching. Having said that, there are big error bars around these divergent states, but I think you raise an important point that our field has always operated under the assumption that if you find anything that shows characteristics of upright locomotion, that it is automatically, by definition, a hominin, meaning it's an ancestor or extinct relative of us, and would be more closely related to us than to any other of the apes. Um, and I think that assumption is on the table, as maybe not being 100% correct. Because if you had in the late Miocene apes experimenting with different forms of locomotion, including upright apes in the trees, navigating in the trees, they might have some anatomies that look a little more human-like. For instance, Danuvius's tibia, in some ways, not in all ways, but in some ways, looks very much like Lucy's. And I think that is telling us about leg positioning, not necessarily weight bearing on a terrestrial bipedal leg, but an animal that's in the trees and moving with hand-assisted bipedalism, like orangutans sometimes do. Gibbons will do this, siamongs will do this, spider monkeys will do this. But right, it would mean that finding evidence for bipedalism may not be enough anymore to claim hominin status. This is going to be fun as we find more fossils from that 5, 6, 7, 8, 9, 10 million year time period. I think what you're going to see are lots of experiments going on with locomotion, and lots of false starts, lots of places where bipedalism may have been, I say attempted, but it may have evolved, and then that animal died out. It just was not a selectively advantageous form of locomotion in that as a habitat. That habitat changed. So we'll see. Yeah, it'll be fun.
Definitely. I mean, we've talked a little bit about what the fossil record shows us about the origin of bipedalism, and you mentioned this very briefly. There are other kinds of data that we can look at to sort of study the emergence of this kind of locomotion. And you mentioned Laetoli, which is a place I've always wanted to visit. It seems like one of the sort of most iconic sites. It would even just thinking about it kind of gives me chills. So there, it's a very famous set of trackways, and so you're seeing behavior, right, of an animal. And what does that trackway tell us about the evolution of bipedalism, at that point in time, which is what, 3.6 million, compared to what you know about it going back to Danuvius or to something more recent like Sahelanthropus or Auroran?
Yeah. It's bipedalism 2.0. It's a really good biped. Those footprints, and I was at Laetoli in 2019, and yes, it is. That place is magical. That place is just amazing. And there are footprints, in all these ash deposits that are eroding out of the hillsides. And right, like you said, it's bones, fossilized bones are, I love fossils, and these are wonderful, and we can squeeze information out of them and tell stories about what our ancestors were like from these bones. But footprints are alive. They're telling you about this moment in time in the life of a living, breathing, thinking individual who was a lot like us. And a lot of the recent biomechanical work that's been done on the Laetoli footprints is telling a story of a very human-like biped. It's something that's moving a lot like us. It's not hunched over, crouched down, bent hip, bent kneed, like a Groucho Marx walk or like a chimpanzee moving on two legs. This is something that from a distance, it would look like you and I walking. Now, if you could put it on a treadmill, if you could put an Australopithecus on a treadmill, you'd pick up some subtle differences probably. And that's a fun thing to think about because you can't ever put an Australopithecus on a treadmill. But from the footprints and from the bones, It looks like they're not pushing off the big toe quite as much as we do. Their arches are a little flatter than ours are. Their legs are a little shorter, um, and they're maybe not extending at the hip quite as much as we do when we walk. But those differences are subtle. But one of the really, I think, amazing discoveries of the last 10 years is that we often will think of bipedal evolution in a linear way. I even just did it talking about bipedalism 2.0 in Australopithecus. But what we see instead are different forms of bipedalism evolving in different species of Australopithecus. And so at the same time, Lucy and her species were around, and her species was making those human-like Laetoli footprints, there was another species that had a divergent big toe that was in Ethiopia, not far from where Lucy was found, climbing trees and walking in a biomechanically very different kind of way. This was a fabulous discovery made by Johannes Haile Selassie in Ethiopia in 2009, and showed that there were these different forms of walking coexisting. And then behind me, this skeleton here was discovered by Lieberger, and actually the first piece is by his 9-year-old son in a cave of Malapa in South Africa, also in 2009 is when they were published. 2008 was the discovery. And I've worked on the foot and the leg of this skeleton. And when I first started working on it, to me, an Australopithecus was an Australopithecus. I'd just finished my PhD. I'd studied the foot and ankle and leg of hominoids and hominins, and I'd seen all these Australopithecus fossils. And to me, there was variation, but not functionally meaningful variation until this thing. And this thing was so different from any Australopithecus I'd ever seen, with its heel and its ankle and its knee, and aspects of the hip and the lower back, that we've hypothesized that it walked in a very different kind of way than Lucy and her kind. And what's neat is that this carries right up until the Pleistocene. And even on the doorstep of Homo sapiens, you have Neanderthals in Europe, Denisovans in Asia. On the Indonesian islands, you have Homo floresiensis and now Homo luzonensis. And then right in South Africa is this brand new species named in 2015 called Homo naledi. And so there were all these different species and populations coexisting. Some of them we interbred with. Some of them I don't think we probably did. But from the foot bones and the leg bones, it looks to me like many of them walked in these biomechanically slightly different ways, or these different flavors of walking. So I love to sort of think about jumping in a time machine and going back to any of these time periods, and you'd see these different kinds of us, different species of our ancestors, and they'd not only look a little different and maybe be eating slightly different things, but they'd be walking in slightly different ways.
Yeah, it's really wild to think about that degree of experimentation occurring for the vast majority of human evolution, not just something that happened in the Miocene when it was Planet of the Apes and bipedalism was first appearing, but right up until virtually yesterday in geological terms.
That's right. It's amazing. And when I was in grad school at the University of Michigan, the story very much was Homo erectus right up to Homo sapiens, and then what do we do with Neanderthals? And that's what we all argued about. Were they different species, or were they part of our heritage? And now, so to me, studying upright walking, the Pleistocene wasn't really interesting. We had already evolved human-like bipedalism. So let's go back to the Pliocene. And no, the Pleistocene is really interesting. There's a lot going on there.
Yeah. If we go back to Laetoli and the sort of earliest evidence we have of hominins walking more or less like we do, it's interesting that the oldest known stone tools are just a few 100,000 years younger than those footprints. So we're getting a little bit closer to what Darwin was talking about potentially, right? And I'm just wondering sort of like how you see that how you see things aligning there. Could it be that this bipedalism 2.0 is what frees the hands to start doing stuff like making stone tools?
I think that possibility again is back on the table. And this was, Darwin's idea about bipedal origins. He also incorporated brain size enlargement, which we know now is probably not part of the story. That does indeed happen later. But you're absolutely right that if you go back to the 1970s, 1980s, we had the Liatoli footprints at 3.6 and the oldest stone tools at Olduvai Gorge at 1.8. And it looked like Darwin was wrong. It looked like the two are just chronologically not aligning. And then there were stone tools found at the site of Gona that are 2.6. Okay, 3.6, 2.6, we're getting closer. Human-like bipedalism did get pushed back thanks to a tibia discovered by Maeve Leakey. It's about 4.2 million years old, and it's very human-like. I'd love to see what the rest of that creature looks like. Australopithecus anamensis, and my honestly, I was going to say my hopes, but my expectation, given how remarkable my colleagues are at finding these fossils, I love being out there looking for them, but they're much better at finding them. I think about Johannes Haile Selassie, who has just made extraordinary discoveries in Eastern Africa in the last decade or so, last 2 decades. And so knowing more about that creature, I think is going to be really important. But back to your point, we now have at least reports of stone tools at 3.3 million, and they're controversial. But at that same time, 3.3 million, Australopithecus afarensis, to me, behaviorally, I don't see any reason why they wouldn't be making stone tools. They're walking like us. There is slight brain enlargement compared to Ardipithecus, say it's about a 20% increase in brain size. And there's that new discovery on the basis of the Dakika child, a juvenile skeleton, that shows that they had slowed down brain growth. And slowed down brain growth is tied in mammals to learning and relying very heavily on learning. And this is a horrible idea for a slow biped, but also something that is going to be heavily predated upon in the environment. You'd want to speed up your growth rather than slow it down. And there were plenty of carnivores on the landscape that were more than happy to eat an early hominin. So the fact that selection was favoring slowed brain growth, to me, tells a story of heavy reliance on learning, and learning what? Learning how to be an Australopithecus, and that might have involved learning how to make stone tools. But it also is a story of cultural buffering and social buffering. That how do you ward off, how do you survive on a landscape like that when you're slow? How do you avoid just being picked off by the leopard all the time? Is that you look out for each other, you have each other's backs. And so I think our sociality is built into bipedal locomotion. The bipedal locomotion simply is not going to be an evolutionary success unless it happens in something that is either super fast, like an ostrich, or is super social, and even compassionate and empathetic, like we are.
Yeah, I mean, I thought that was a really fascinating point that you made in the book, where you start out by talking about, early ideas linking bipedalism to, violent behavior in hominins, to now, you making the argument that actually it could never have worked if our ancestors didn't have the capacity for empathy and cooperation.
I think so. I think that idea about uprightness, freeing the hands, not just for tools, but for weapons, is still part of the popular culture. We've all seen 2001: A Space Odyssey, right? The beginning there with the wielding of the weapons, and that has its intellectual roots back to Raymond Dart, who discovered the very first Australopithecus, the tongue child, who's just over my shoulder here, this wonderful little fossil. But later in his career in the 1940s, post World War II, he worked at a site called Makapansgat, where he discovered bones that had been smashed, and he formulated a hypothesis that the hominins themselves had been doing this, that we were these bloodthirsty killer apes. And that idea has had roots, and is still sort of, again, part of the popular culture, even though we know now that at that site of Makapansgat, those bones were smashed up because of hyenas. It wasn't us. So the science has refuted that idea, but it's still part of how we think about ourselves. And instead, I draw attention to a fossil like this, discovered in the 1970s by Richard Leakey and his team in Kenya. And this is a leg bone, an upper leg bone of an early hominin. It's about 2 million years old, a little short of 2 million years. It's got that long femoral neck. That's how we can tell it's from an upright walker. But the cool thing about this fossil, the amazing thing about this fossil, is it has a healed fracture. So this bulge of bone sticking out of the medial side of the inside of the femur, that's a healed fracture. And think about breaking your femur 2 million years ago. No hospitals, no doctors, no fire, no shelter. And you break your leg, but you heal, you survive? That can't happen unless other individuals are helping you out. And it's not just 2 million. That back to Lucy's species, there's a second skeleton, known as Katanumu. And he's about 3.5 million years old, large, we think it's a large male, and he has a healed ankle fracture. So again, he stepped in a hole or he fell out of a tree, something happened, and he broke his ankle. Now, if you're a zebra and you break your ankle, that's not a good situation, but you're still able to get from point A to point B on your 3 legs. If you're a biped and you break your ankle, you're already slow, and now you're hopping around your landscape. I don't see how you survive. And yet this is a healed fracture. So that individual did survive. And again, it's connected intimately to bipedalism, that these vulnerabilities that we have as bipeds, but then the fact that we have injuries that make us particularly feeble if as bipeds, is, again, I think explainable only if we were and continue to be empathetic and compassionate and generous and pro-social with one another.
It's fascinating. I know Nell has some questions from the audience that she wants to put to you, so we'll turn it over to her.
Hi, thank you. I hadn't heard that about the Australopithecus with the healed ankle. That's amazing. I had no idea that it went that far back. Sorry, that's just
well, no, so that was a discovery. It was a discovery in 2010.
Okay.
It's 11 years ago now, but still, it's an indication of just how rapidly my colleagues are finding these fossils and putting them out there. And each of these fossils has this amazing story to tell about why we are the way we are today. So it's easy for one to get overlooked. And that's a cool fossil. And that one definitely, I think, didn't get the attention it deserved.
Yeah, that's amazing. Because while I'm looking through these questions, but yeah, I feel like the memory that I have of it are sort of that the last I heard, there wasn't evidence of that until like Homo habilis or something. So the idea that anyway, sorry, that's awesome. It's nice to know that we can be nicer than we think, and that goes back longer. That's just very reassuring. We have a question from, let's see here. If you were able to change human anatomy to make bipedalism easier on us, what would you adjust?
Oh, the foot. The foot's a disaster. I mean, I study feet, and the foot is sort of like, evolution's example of a good try. It's like you did your best, but But what happened here is you converted a grasping ape foot into something that needs to be rigid, and to yes, have moments of flexibility, but also then push off the ground in a rigid way. So we have the same 26 bones in our foot that chimpanzees do. So imagine you're trying to create something from scratch, and it needs to be able to contact the ground, absorb elastic energy, and then kick off the ground into your next step. And you make it out of 26 parts. Like you'd fail that engineering course. It just wouldn't happen. So look at this. Now there you go.
Yeah.
So here's a foot from an ostrich. And what's happened over the course of avian evolution, bird evolution, is that the bones that make up their ankle and foot have fused together into a single rigid structure that is composed of, instead of 26 bones, it's about 8 or so in the foot of an ostrich. And this ends up looking a lot like the blade prosthetic that that a lot of para-Olympians will use and use with great effect, and can run very fast. And so, I'd change the foot. Now the back is a bit of a mess as well. But I work more on the foot, and so that's the first place I'd go.
Okay.
Oh, and the knee's a disaster as well, but we'll stick with the foot.
Okay. Kind of to branching off of that, we have another question. Do you think, so the question's kind of, is it possible for bipedalism in humans or anywhere else to evolve and improve anymore, to sort of do we represent the zenith of what this is going to be? Is that even possible to speculate on?
It's a great question. It's the kind of thing that I love to talk to my students about and speculate about. I don't think so. If you look in the Pleistocene at all these different sort of body forms that existed, I don't see the human body today, Homo sapiens, as having some advantage over some of those others. Homo erectus, for instance. With Homo naledi, it looks like the joints were smaller, and so maybe their home range wasn't as large. But I certainly don't think that we have reached some pinnacle of bipedal locomotion. And again, I'd much rather have the skeleton of an ostrich if I wanted to get from point A to point B on 2 legs, or a T-Rex for that matter.
Right.
And even if you look back in the past, one of the really fun things that I got to research writing this book were bipedal animals that have long gone extinct. For instance, there's a crocodile known as Carnifex carolinensis, discovered in North Carolina by Lindsay Zano, who's a vertebrate paleontologist at North Carolina State. And she, at the museum in North Carolina, and she reconstructed the gait of this ancient crocodilian as being up on 2 legs, at least occasionally. So imagine a 9-foot tall crocodile that would jump up on 2 legs and could sprint. No. This sounds horrifying. And yet, what I find fascinating is that didn't have evolutionary legs. Yeah. What happened to crocodiles? Well, they're on all 4s, and they're stealth hunters, they're ambush hunters. So being bipedal was not evolutionarily successful ultimately. Being quadrupedal was. And you see that in dinosaurs too. The earliest dinosaurs were bipedal. And then, Apatosaurus and Brontosaurus and Brachiosaurus and Stegosaurus and Triceratops, those are quadrupeds that evolved from bipeds. So bipedalism seems to pop up occasionally and honestly fail. And either convert to quadrupedalism or be a dead-end lineage.
Could you brought this up in the conversation, but maybe just as kind of a reminder, but so if bipedalism arose gradually, and it sounds like it did, what's the time span? How many millions of years, or what's the time span generally?
So we don't know. It's really interesting. It depends entirely on what the body form of that common ancestor looked like. because if it was a knuckle walker, if knuckle walking is the ancestral trait, and chimpanzees and bonobos have retained it on their lineage, gorillas retained it on their lineage, then you would have to have intense, rapid natural selection to go from a knuckle walking common ancestor to something that is not just getting picked off by leopards because it's hunched over and can't move either quickly or efficiently. So it would have, in that circumstance, I foresee this happening incredibly fast. Okay. Or it happens incredibly slowly. Yeah. If the common ancestor is something that is, imagine more of like a large gibbon with shorter arms, or a smaller orangutan-like thing up in the trees, moving on two legs. And then as there is environmental change and you begin to get patchier forests, it has to move across that landscape on its two legs, but it already has a body form to do that. Mm-hmm. And so it's not a new locomotion, it's an old locomotion just in a new setting. Yeah. And in that case, it would be very gradual. And what we would be looking for, I think, are anatomies that are not from an arboreal biped, but something that is a terrestrial biped. And we haven't even thought what that would be as a field. How would you distinguish between something walking on two legs on the ground, very different kinds of forces, versus something moving on two legs, hand-assisted bipedalism in the trees, where the trees are more compliant? So the forces would be really different. You probably wouldn't have to have those hip mechanics because you're holding your body with your hands. Yeah. And so you're not going to have that pelvic tilt problem. And that's something we as a field, haven't really grappled with.
It must be hard. I would think that just in contemplating these different scenarios, that it would be kind of easy to sort of fall into sort of a Lamarckian trap about some of these, right? It's sort of the way that you're, I don't know, maybe by the time you're in your position, not, but like, I don't know, for the layman, that would seem like it would be a pretty easy trap to fall into.
Now, so I'm a Darwinian gradualist, and I, I think this probably happened gradually, and I think there's probably not one explanation for why bipedalism was selectively advantageous, that it was a host of things, and our efforts to search for the answer is probably pretty wrong-headed. However, so yes, you've got a population and there's variation, and there's certain individuals that move bipedally more than others, and they end up having more food and more reproductive opportunities, and off you go. And we're just trying to figure out what it is that allows those individuals to have more food and those reproductive opportunities. Okay. There are other scholars that think this was more Lamarckian, that this was, so Richard Dawkins has written about this, that he thinks bipedalism emerged as sort of a meme, that it was just, a cool thing to do. And that, chimpanzees, gorillas occasionally move on two legs. Mm-hmm. And if that sort of became, for some reason, the fad in that population, then you could have more and more individuals aping each other, which is what we do, right? And because bone is plastic to an extent, you might get some of the anatomies that then are really key to bipedal locomotion, not because you inherited them genetically, but because you acquired them through your life. And so the best example of this is at the knee, that when you're born, your femur is perfectly straight. But as you start toddling around, your femur begins to angle in and you become knock-kneed. But we're not born that way. And so when you find a femur, as Don Johansson did in 1973, and it has an angle to it, it tells us that this individual had to have walked on two legs. Yeah. Because there's no other way to get that angle. So there is this really cool combination of anatomies you're born with and anatomies you acquire that blend together in your musculoskeletal system that allow you to move on two legs.
Man, okay. Well, thank you. We have Matthew St. Ange asking, what circumstances are making it easier to find more fossils today?
Oh, great question, Matthew. Great question. So like any science, you build on the work of previous generations, and there are lots of you know, false starts that happened and mistakes made, and you learn from the mistakes of predecessors. But having said that, there's also a lot of technological advances that are happening. And so, for instance, in South Africa, one of the reasons that my colleague Lee Berger has been able to find as many fossil sites as he has is by using satellite imagery and looking at the clusters of trees that grow out of caves. When you're on the landscape walking, it's really hard to see these caves, but from the top down, you can see them, much better. So that's one of the things that's happening. I also would argue that the decolonization of the science, especially in Eastern Africa, has played a huge role in this. And that instead of doing parachuting science and dropping into these places and spending a couple of weeks and then going back to the United States or back to Western Europe, a lot of this work now in incredible fossil discovery is being done by individuals that are from those countries. So Johannes Haile Selassie and Zerai Lemsged in Ethiopia, Charles Masiba in Tanzania, Chalo Manthi in Kenya, and many other folks. I don't. So Kate, I'm curious what you would think about that. Why do you think we're getting this
I mean,
explosion in
for the
discoveries?
reasons you described, but also I wonder if there's like a little bit of a snowball effect of like, oh, Lieberger went into like the cradle of humankind, which was already supposedly really well explored, and found these amazing things. And so maybe we all need to kind of like start going back to places that we thought didn't have any more fossils for us or that we haven't looked at yet. And, you know, kind of go in there with a fresh eye and fresh outlook.
Yeah, I agree. I think that's true. And yeah, that assumption that we'd already, that many of the great discoveries that had already been made, again, this last 10 years, I've just been astounded by the number of fossils, and not just the number. It's not like we're getting more of what we already knew about. That's happening to some degree. But we're also finding, or my colleagues are finding things that I don't think any of us could have predicted. I certainly wouldn't have predicted Homo naledi, Homo floresiensis, Australopithecus sediba, any of them. So it's been this really this wonderful awakening, I think, in our field, and and a dose of humility that there's a lot out there for us still to discover, and a lot of our ideas are going to end up being wrong, and that's okay, as long as we are following the evidence. Then it's okay to have an idea based on the evidence you have, and then, oh, look at this new fossil. Now it shows I was wrong. Oh well, great new fossil.
It's exciting. I think we can leave it there. I think we're about at time. Thanks to both of you so much, Jeremy and Kate. Thank you. This was fantastic, and thanks to you for joining us. Please learn more about this incredible book at I've posted the link in the chat, harvard.com/book/first_steps. There's also a link up there to donate. Thanks so much for tuning in, and stay safe. Have a lovely night, and thanks again to both of you.
Thanks, Nell.
Thanks.